Today in Crosby's class, atoms. Everything in the world is made up of atoms. Take, for instance, this cell phone. If you were to zoom in with a microscope, you would see billions of atoms. If you were to zoom in on one atom, you would see something similar to this. All atoms have a nucleus made of positively charged protons, neutrons with no charge, and then there are electrons, which have a negative charge, orbiting the nucleus. For right now, we're going to focus on the electrons. Electrons like to be in certain sublevels, of which there are 4, S, P, D, and F. A way to remember this is smart people don't forget. Each level holds a certain amount of electrons. S holds 2, P holds 6, D holds 10, and F holds 14. The quantum model of the atom explains this. The quantum model is set up on your basic y-axis, x-axis, and z-axis, which demonstrates the third dimension. The energy level 1 has a sublevels of S, which holds 2 electrons. The next level is 2. It has 2 sublevels. One is called 2s, which holds 2 electrons, and one is called 2p, which can hold 6 electrons, one in each half of these peanut-shaped orbitals. One way to know how electrons fill up these energy levels is by the diagonal rule. This shows the lowest energy levels in an atom. Each higher level has one more sublevel than the previous. The red diagonal arrows show how the electrons fill the energy levels from the lowest to the highest. This is the reason it's called the diagonal rule. To see this in action, let's work with an atom called magnesium. Magnesium has 12 electrons. Now remember the diagonal rule. 1s holds 2 electrons, 2s holds 2 as well, 2p holds 6 electrons, and the last 2 electrons fit perfectly in 3s. You can write these numerically. When you do that, you've got electron configuration. But we're not finished. For the final step, you look at the highest energy level, in this case 3. From here, you take the electrons in the level. You could write some lengthy spiel if you really wanted to. Or you can just write valence electrons. These valence electrons are portrayed in the dot diagram. Let's do another example with chlorine. Chlorine has 17 electrons. Keep in mind the diagonal rule. Chlorine can be configured similar to magnesium. It's when we come to the final electrons we run into a difference. The p sublevel can hold up to 6 electrons. Even though there's only 5 electrons left to configure, they will still be distributed to the p sublevel. The outer level just isn't filled. Because of this, chlorine isn't as stable as it could be. The valence electrons for chlorine are the combined electrons from the 3s and 3p orbital, as they're both the highest level. The dot diagram for chlorine will look like this. Notice how it's missing 1 electron to be perfectly filled. To be stable and happy, chlorine wants to fill this slot.
Diagram!
Let's say magnesium drifts close to chlorine. Since magnesium has 2 valence electrons that it's willing to give up, chlorine will attempt to steal one. Like a lasso, chlorine will pull at one of magnesium's valence electrons. Though it puts up some struggle, chlorine will gain the valence electron it wants. Now chlorine is stable, but magnesium still has 1 valence electron it doesn't need. Another chlorine will come along and, through the same process, gain magnesium's last unwanted valence electron. Now all 3 atoms are stable and happy. Magnesium, since it lost negatively charged electrons, is a positive ion. Both of the chlorine atoms, since they gained electrons, are now negative ions. Since opposites attract, magnesium bonds with the 2 chlorines in a process called ionic bonding. The result is, drumroll please, an ionic compound called magnesium chloride. We can shorten magnesium chloride by converting it to its empirical formula.
What does this mean?
It's the ratio of the atoms in the compound. For every 1 magnesium, there are 2 chlorines. In other words, magnesium is used in the process of making tofu.
Soy milk. And is used as an anti-ice.
It isn't for consumption,
but it won't kill ya if you get the munchies.
It's also non-flammable, which is typically spelled with 2 M's.
I wasn't recording yet!